Joe, you're on mute.
Yeah, sorry. Will I never learn? Good afternoon, everybody. Sorry about that. Bit of a false start there. Well, welcome everybody to our final workshop in the Retrofit series. This afternoon, we're going to be talking about smart homes, smart meters, Internet of Things, all that kind of stuff. My name is Joe Flanagan. I'm the project manager for the Energy House 2 project, which is the new laboratory we're building at Salford, which you can see on the backdrop behind me. That's from our live webcam. I just grabbed that earlier on, so you can see we've got a roof on there, and we're just about putting up the walls and the cladding, so it's all progressing nicely. Anyway, as far as this afternoon goes, we've got a very interesting lineup of speakers, all experts in the field. We've done these workshops previously over 2 days, so you're getting a very cut down, highlighted version here of the 2-day one that we've done previously. I'll just run through some of the housekeeping things. Please keep yourselves on mute. Any questions, submit through the chat in the usual way. If you've got any technical issues, direct message Helen, who's our moderator stroke producer today. And we will be recording the session, so if you don't want to be seen, just keep your video off. Yeah, I think that's all the housekeeping. So in terms of today, we've got a number of interesting speakers, and I've lost my agenda, so I can't tell you who. Here we go. Right, so kicking off with my colleague Yanis, who runs the Smart Meters Laboratory here at Salford, and Yanis will be telling you a little bit about that. We're then going to give you a bit of background around the electricity supply network, which is vitally important in this agenda. I mean, we're all about saving energy, saving electricity, saving cost. And Nigel, who previously worked for Electricity Northwest, will give you a description of that. We've got Carolis, who we've worked with quite extensively over the past 12 months. We'll be talking about energy savings by making use of time of use tariffs and agile tariffs. Bit of a break, and then Matt will be telling you about some of the products and services for smart homes, and then Jose will finish off by telling you about a home energy management system, and then we'll close with Yanis and wrap up with any questions that we missed along the way. So that's this afternoon's agenda. I hope you all enjoy it and you get something useful out of it. But before we dive in, I've got a couple of polling questions just to keep it kind of interactive and just to see how this is going to work for you. So first one, how would you rate your knowledge of smart technologies for the home? So if you could just fill in that, going from very good to I know nothing. And number two, what do you think the potential is for energy saving through using smart technologies? Very good, down to nil. So if you just have a go at that and submit, please, and we'll just see what kind of level of knowledge it is among our audience at the moment. Okay, can we, is everybody submitted? Can we share results? So, in terms of knowledge, okay, not many people with very good, which I guess is to be expected. If you do everything, you wouldn't be here. Nobody knows nothing, which is good, and an even split between good, fair and poor. So that gives us a measure of the audience, fairly mixed view. And what do you think potential is for saving energy through smart technologies? Unfortunately, I can only see the top two. Let me just bear with this. Right, everybody thinks it's very good, good or fair. Nobody thinks it's poor or nil. Good, so we've got an audience there who's well attuned to the fact that we can save energy through smart technologies. And with that, I shall sign off and let Yanis give you an intro to today's session. Thank you. Bye-bye.
Good afternoon. I was muted as well. Good afternoon. Welcome to the fifth and final part of the domestic retrofit webinars. I hope you have enjoyed all sessions until now. My name is Ioannis Paraskevas, and I'm running the Smart Meter, Smart Homes Research and Innovation Lab. The Smart Meter, Smart Homes Lab is part of the Energy House Labs. And as Joe mentioned earlier, today's session will focus on what we believe is a cutting-edge and very interesting area, focusing on smart home technologies for energy, cost and carbon, of course, savings. We have four very, very interesting, we believe, sessions that will be presented by four excellent speakers. The first session will provide us with an overview of the electricity supply network, general description, general features. The second session will focus on the utilization of time of use tariffs for cost saving and energy saving for heating. The third session will focus on new novel products and services of the smart home again for energy and cost saving, and we are going to close with a cutting-edge product on home energy management systems. I hope you will enjoy all four talks, and we will start with the first talk that will be presented by our first speaker, Nigel Blandford. A few things about Nigel. Nigel's early career path was in renewable heating. More recently, he worked at the district network for the district network operator Electricity Northwest. And now Nigel is a research assistant with us on the Energy House 2 project. Thank you very much, Nigel.
Thank you. Can you all hear me and see the screen? So someone's going to have to give it to me verbally because I can't see people. So
all good, Nigel.
Yeah.
Thank you.
Oh, good. Excellent. Good to go. So smart home session, our electricity network. So this is going to really give you a very, very basic view. So a lot of you, I'm sorry if you already understand a little bit about the network and how it interacts with our home, may find this a little boring, but I think it's just trying to sort of introduce to let everyone know where we're coming from. So it forms the foundations for the next speakers. So, you know, that's me, Nigel. You know, my background, as some of you know, my background is actually from a sort of, I guess, a natural resources and heating background. But I have previously to working at the university, worked for Electricity Northwest, which was a really, really, really interesting job, working with them to reduce their own carbon emissions and basically working in a lot of their big substations. So these are the larger substations, and it is really interesting. It's like, in many cases, walking back in time, because these buildings are temperature and humidity controlled. A lot of that equipment is very robust, but you know, it's been there for a long time. As a member of the public, you'd never go in there. And you'll see in the background there's a table and a couple of chairs. That's because the engineers will have to come in and do their tests every now and again. So this is just a little diversion, really a little going off a little tangent here. So I had to go around all of these substations. So I got to see more inside these substations than most people would do. And I started noticing, because they're humidity controlled, things last for a long time. And start saying these large substations had to have a table and two chairs. And what I came across was this amazing collection of chairs going back from the 1950s all the way through to the 1970s. Like I say, because of the temperature controlled and humidity controlled environment, they were in a really good condition. I even had a little Twitter page called Chairs in Substations. I mean, these are pretty worth a fortune on eBay. But anyway, I digress. So the electricity network. So once upon a time, our electricity network was based on coal. And we had very few, very large coal-powered power stations. They would be running almost 24/7 and often full on, you know, running at full steam. And that would then go down the electricity network to the electricity meter, your electricity meter in the house. So this is a classic one. Like I said, I used to go around all the substations, and this was one of my favorite ones here. Very old dial electricity meter. And if you look on there, you can see property of the Northwestern Electricity Board. And it was made by Ferranti in Hollingwood, which is, that's the building. I think the Manchester Evening News is now printed in there. So this is a locally produced product, and the serial number F66M, the 66 is I believe, the year of manufacture. So that was the last time that England won the World Cup. So that was the standard meter, but because of this sort of, I guess, the large coal-fired power stations on all the time, you did get high demand during the day, low demand, but still high generation during the evening, the night time. So you'd have these meters like this. So it's got two, you can see the two readings on there. The top one is for the nighttime, that sort of nighttime tariff or economy 7 or whatever you'd like to call it, and the bottom one for the peak demand. But whether it's the meter you've seen there or the previous one, it all came down to, at the end of the day, someone had to come round and read your meter. So the world has changed though. So coal is now on the way out, and that gave way very much to gas. This is it's actually a visualization, but that power station exists. This is a combined cycle gas turbine power station on the banks of the Mersey down near Carrington. So those large coal-fired power stations were generally replaced by large gas stations. But then things changed again. Gas moved on to renewables. So obviously what you're seeing is that these single large sort of power stations, then generation became more decentralized, diverse from wind, solar, and biomass to some extent. And in the home as well. And this is what this is what I'm really trying to concentrate on, is what happened in the home is that we got the smart meter. So if we sort of look in more depth through the keyhole, the anatomy of the smart meter, see what's going on here. So this is the smart meter here. And like I said, the old display was you had to come out and read it. It was a visual display. You still have that on the new smart meter. So you've got the display there. You have to, I think it's A9, I think, is to bring up the consumption data on there. Also down at the bottom, you see that's the sort of proper meter. It's been replaced there. So that's just giving you the details of when the meter was replaced. But you've also got something there. So them double dots there, that's an optical port. So you can put something in there and draw data out of that locally as well. So again, that's a big advance from just as it stands from the previous meters. But what's even more interesting is that you don't have to have someone to come out and read this. This will read itself. So you get a transmission of data here through the secure data network run by the Data Communications Company. You can see that there. And that data will then go out to the energy suppliers, electricity and gas operators, and the authorized third parties. And that arrow point in there, that's a little light on, and that's showing that information going outwards is to the wide area network, or the WAN, and that little, where the arrow is pointing on that last slide, it does say WAN there, and the light is on. However, it does something else as well. So it transmits in the way. So there's also, you may not be aware, but there is a Zigbee network attached to the smart meter, which is transmitting through the house, most commonly connected to your in-home display, but could be connected also to that other device there. That's a consumer access device. So things are going both ways. And there's a little button there where that arrow is there. You can see it says HAN on there. You probably won't be able to see that. That's what it says on there. And this meter is a SMETS 1 meter, and everyone's now moved on to SMETS 2 meters. So yes, the network inside your home is called the Home Area Network, or the HAN. So the thing is that with renewables, as compared to the other sort of generation that you've got, is that wind blows variably. If you've got solar, obviously the sun's out sometimes, it's not out other times, which means that there's more variability. So how do you sort of handle this in the home? Well, on the left here, you see that old meter, that really only just handled the nighttime and the daytime tariffs. Now, the smart meter can handle a variety of tariffs now. This is a bit smarter, it's a bit more flexible. Like I'm saying, it can handle these things, and you'll learn about them, the time of use tariffs. Additionally, you look at the home now. So your home may have PV panels on it. Your home may have a battery to it, and your home will soon or probably have a charging point attached to it, and that will be the largest sort of demand at any single time that you probably have from your domestic supply. And you can also begin to do this bi-directional charging, so you could use that car like a battery to either run your home or run back into the grid again. So what we've seen now is that this is the way the network's gone: decentralized generation, variable generation, got better data transfer, smart meters. We have a home area network. We have infinitely variable tariffs, and we have two-way energy flows. So very briefly, the old model: coal, electricity, through that meter into your home. The new model that we're seeing there is a lot more complex. So you've got renewables, generate electricity, but the home itself has also could have solar on the roof, which is putting electricity into the home and maybe back out again. Batteries going in and out, cars could be going in and out. And the interface for that is the smart meter. And so what you're seeing is that electricity will be going both ways, just not in one direction. And also data is going both ways as well. So this is a big step with regard to what we had not only, 10, 15 years ago. So that's a simple introduction to how the energy network has changed from generator to consumer. It introduces the smart meter to the home and its potential, and there is a lot of potential for the smart meter, and it sets the scene for the following presenters. So I hope that was a nice, simple introduction for you. Thank you very much. So do we have any questions? I can see one there. Is the data from the meter on the Zigbee network freely accessible to the householder and or others to use? Is it real time? Well, you have to access that, and generally you would use something, and someone will be talking about that, a consumer access device. So you can get that data. Your in-home display will just sort of kind of display what you're using at the moment in terms of gas and electric, but the actual data and some of that historic data can be pulled out of there. So yes, if you've got a consumer access device and it's paired with the smart meter, it can be used. Another question: infinitely variable tariffs or changing every 30 minutes? I guess, yes, it is actually on a, I say infinite variable. We do in the UK bill, or what they call settle, on a 30-minute basis. So yes, it will always, I guess, be billed on a 30-minute basis. But what we're seeing is that those every 30 minutes with a tariff like Octopus Agile will change every 30 minutes. And yes, there's advantages and disadvantages of that. Octopus are sort of going ahead and telling you kind of 24 hours in advance what that price will be. So yeah, for some people, particularly if you're a large user, like you've got an electric vehicle, it's going to be advantageous to you to know when that electricity is going to be cheap. If you've got a battery, then use that rather than pull electricity off the grid during the expensive period. So any more? If there's no more questions, I think I will hand back to Dr. Yanis Paraskevas.
Thank you very much, Nigel, for the very, very interesting talk that you gave us. I would just like to add to Chris' question. Nigel already covered the CADs. So yes, you can access our data through consumer access devices, as Nigel mentioned, and the granularity can go as low as 1 minute using a certain API technology, or even down to 10 seconds. On top of that, the consumer can access their data directly, sometimes through the energy supplier. For example, Octopus Energy has their own portal that the consumer can access their consumed data, however, in 30-minute granularity. And also, we are going to have dedicated, very sophisticated portals like the energy portal. Matt, who is going to cover not the next session, but the one after it on products and the services for the smart home ecosystem. Is the CEO of this portal called Energy N3 RGY, and he's going to mention more things on how someone can access their data using the portal. So thank you very much, Nigel. We are continuing to the next talk, which is on energy savings on heating using time of use tariffs. Our next speaker is Dr. Karolis Petruskevicius. I hope I pronounced his surname correctly. We have worked with Karolis in various projects. Karolis is head of smart home at Evergreen Energy, and previously was founder of Homely Energy, a smart thermostat company integrating heat pumps with variable electricity tariffs. Karolis holds a BSc degree in economics and a PhD in power networks. Karolis has previously interned at Goldman Sachs in sales and trading. Thank you very much, Karolis.
Hello, everyone. Thank you very much, Giannis, for the introduction. If it's okay, I think Giannis did a great job in introducing me, so I don't think there's anything else to mention there, but do have some slides, so I'm just going to start off there. Just need to share my screen. One second. Share. Okay. Can everyone see the slide?
We can, thank you.
Okay, great. Great. So as Giannis said, at the moment, I'm the head of smart home at Evergreen Energy, previously a founder of Homely. Homely has been acquired by Evergreen Energy this summer, so we're continuing our work in the same field, just providing it as part of Evergreen Energy. Quick session overview. So I'll do a quick introduction on what Evergreen Energy does. I'll talk a little bit about the electrification and dynamic tariffs, introduction to heat pumps and Homely controls. I'm not going to delve into too much detail on heat pumps. I wasn't on the sessions yesterday, the previous session on the heat pumps, but I think that that would have been explained quite well. And then I'll just talk a little bit about the dynamic tariffs in action. So Evergreen was set up with an aim in helping the UK achieve its carbon ambitions. We're an installer of renewable heating systems, such as heat pumps. We're also making the systems more affordable through assignment of rights propositions, reducing the cost of the heat pumps to similar to the cost of a replacement gas boiler. We provide support, advice, and design tools for around 35% of all MCS approved organizations. We're also now the makers of Homely Smart Thermostat. Smart Thermostat specifically designed for heat pumps that connects them to variable electricity tariffs and provides the ability of tracking the performance to the installers. So I'll just do a quick intro in terms of why we're here and why we're talking about heat pumps. So Manchester, for example, is aiming for net zero by 2038. To achieve this kind of ambition, we'll need to see a significant change in the way we heat our homes, moving predominantly from heating our homes with gas boilers to a combination of electric heating, including heat pumps, district networks, and potentially hydrogen. In this workshop, I'm going to be talking a little bit about the problems associated with the electrification of heating and how a combination of the smart tech and the tariffs can help us overcome these. Again, a few numbers to get us going. So at the moment, this might be slightly out of date, but it was around 180,000 heat pumps installed in the UK in 2020, with that number growing rapidly in the next years towards the 2050, 2038. The numbers in the slides here have been taken out from the future energy scenarios. So National Grid provide the potential scenarios of how we're going to achieve our energy ambitions. In line with the heat pump changes as well, there's a change in the way that we generate our power, and we're looking to see a huge increase in the amount of power that we're going to be generating from renewable sources such as solar, wind, doubling in almost all national grid scenarios by 2038. Even though heat pumps are a great way at reducing carbon emissions, so nearly 2 tons of CO2 can actually be saved per heat pump per household per year. There are some limitations in what our current electricity system infrastructure can handle. So if we were to imagine, for example, that all people were, if we were to assume that heat pump change would happen tomorrow, for example, and let's say that 12.5 million heat pumps were to be plugged in these homes at similar times of the day, just because majority of people have similar profiles where they go to work and they come back home, or at least we used to. That would cause some concerns in terms of how the network is managed, and basically the power that we need to push through the networks would make it really difficult. We'd also need to consider that heat pumps are not the only load that we're trying to electrify. So we're electrifying we're seeing the increase in electric vehicle uptake. And as you add on all of these different loads that are supposed to be going on the electric networks, we can see that without smart management of them, we can see sky-high peak demands requiring us to build more power plants, lay more cables, and pay potentially more for our electricity in the future. Alternative to building additional infrastructure is, we believe, smart control of these devices. So as an example, by using smart heat pump scheduling and smart vehicle charging, we can smooth some of these demands. So even though we all want our houses to be warm at, let's say, in the morning when we get up around 7 till 8 o'clock in the morning, and when we get back home, 6 till 10 o'clock in the evening, there is a way how these loads can be managed throughout the day and shifted around. So you can start using houses, for example, as batteries. So you can overheat it slightly during the off-peak periods where the electricity prices are slightly lower, and coast through the more expensive periods, smoothing out that demand curve throughout the day. This in turn reducing the customer bills and the need for network reinforcement, as well as increasing the use of renewable energy, as some of those loads can be shifted to the periods of high power production from renewable sources. Quick explanation of how the electricity, how the actual domestic bill is actually created. I thought this was quite interesting, is that the wholesale price of electricity, so this is the cost of electricity that an energy provider, a power plant would sell that power to the electricity supplier, is only a fraction of the actual electricity bill that we're paying. So at the moment, the wholesale cost contributes to around 32% of the whole electricity bill that we're paying to the electricity supplier. And the other components, the other major components include the network costs and operational costs and some other levies the electricity supplier would need to add on to the bill that we're paying. Therefore, even so, when we're looking at the power production from renewable sources, even though it could be a lot cheaper, it might not mean that we're getting straight away that full benefit, just because there are other additions to that cost of electricity that we're paying, which we need to account for. As an example, so I'm an Octopus Agile customer, and during the 4 till 7 period, during the 4 till 7 p.m. period, there is a premium charge of around 12 pence per kilowatt hour. And even if the cost of electricity, for example, would be much lower, the wholesale cost of electricity, if there was a lot of wind, for example, being produced at the time, that cost to myself would still be significant, just because there is an addition of the 12 pence per kilowatt hour, and that is to account for the network charges. when everyone is using the electricity, that's the period when we need when we get a premium on the network use charges. And just a couple of examples on how the couple of examples of how the power price actually changes with where the actual power production is coming from. So in this graph, we have power output by different power production methods. So coal, solar, wind, gas, other. And we also have price on the right axis, which is the black line over here. And we can see how that varies quite significantly throughout the day. So this is agile price overlaid over the power production composition. And we can see where the period where there was a lot of wind, the price of electricity actually turned negative on this particular day. So 2019, December 8th, we actually saw that agile prices were going negative. And then during the 4 till 7 period, even though there was a lot of wind being production, we can see that the price of electricity increased significantly. And this is, again, coming back to that premium price that we need to pay during the 4 till 7 period. There are, of course, other days when the prices are not as favorable and you don't get paid to use electricity. So in the previous example, agile customers actually and homely customers, their heat pumps were automatically turning on during the night just because they saw that opportunity to take advantage of those low cost periods. But on other days, that's not as favorable, although there are still these pockets of electricity that are cheaper than the average throughout the day. So again, in this particular day, we can see that the wind production was much lower than the previous example. And what Homely here would do is it would try to pick out these cheaper pockets of electricity and kind of try to dump as much heat as it can during those periods to coast through the more expensive parts of the day. That's a quick introduction into kind of how it all comes together with the dynamic tariffs. Is there any questions at this point that I could clarify just before I move on to the next part?
There's a question coming from Julian, which says, would it be sensible to shift the environmental and social obligation costs to gas as a fossil fuel?
That's, from my personal opinion, I would like to see electricity prices being lower, because it is the way that we can we're trying to decarbonize, and that is one of the routes that we can take is through that electrification of everything. I'm not sure whether I can say that whether I would like for those levies to be shifted on gas. I would like to see the difference between the electricity price and gas change in terms of that. At the moment, for example, the electricity price that we were fixed cost of electricity, I think the last time we were trying to compare those was around 12 pence per kilowatt hour for the electricity and around 3.5 pence for gas, which is quite difficult for the heat pumps to compete then in that area, even though they're achieving say 3.5-4 units of heat for every unit of electricity that they're consuming. There's still that it's quite a difficult position to be in. But yeah, sorry, I don't think that I've answered the question. I would like to see there being more of a change in the way that the gas is charged and the electricity is charged.
No problem. There's another question coming as well, which says, wouldn't it be far more energy and cost efficient to store heat in the system rather than the fabric of a dwelling? The storage could be made more cost effective if provided at a community scale, particularly as in the future there might be fewer privately owned EVs parked adjacent to dwellings.
We have looked into some some projects where they are considering a community scale storage. So I think that there are, in terms of storage, alternatives to storage of heat, for example, moving away from actually storing it in the fabric to other mediums. So a couple of options that we've looked into was the buffer tank storage. So a thermal storage where you, for example, would have a 1,500 liter tank and you would try to overheat that using the heat pump during the cheaper times rather than overheating your house, and then using the heat calls from the buffer tank into the house during the times when you need it. There is a case for that where that could work. The couple of complications that you get into is that you need heat pumps work at most efficiently at low temperatures, which would mean that if you're trying to store more heat into the buffer tank, you need to take that into account. But that is something that we've done, and we have an optimization for specifically that scenario, and we can do some more analysis basically on for what house that would be a feasible option. In terms of storing heat in at a community level, in terms of electricity, that is potentially an option. I think the last time I've looked into it as part of Homely, there were some issues in terms of how the electricity is charged. So when it goes through your electricity meter, there are some options around that, but it's quite a new area. Does that kind of answer it?
That was my question, and yes, thank you. That does answer it.
Is there anything else just before we move on?
There's just a general comment saying it's complicated to do without significantly disadvantaging many parts of society.
In terms of the gas and gas levies.
I'm not sure what you're referring to.
Helen, sorry, I think it was a response to the question of Michael. The earlier question of Michael, that was a response from Matt. So I don't think it is a question or a comment for Karolis. Thanks.
It is referring, I'm assuming, to the levy on the gas rather than the electricity. Is that the one?
Yeah, sorry, I was just commenting on the original question. Because gas covers 76% of properties today, shifting those prices between the tariffs between electricity to gas has unintended consequences if it was to be done. So it's quite a complicated activity to do.
I completely agree, and that's why I couldn't really answer it fully, just because there are quite a few factors in there that we need to consider.
Indeed.
Great. So should I then move on to the next part, or is there anything else?
Please move on.
Great. So heat pumps. I'll just do a quick introduction. As I said, I think that there were quite a few sessions explaining what heat pumps are, but just to explain why Homely is a little bit different, I think it's important to understand what is the difference between the boiler and the heat pump. So this bit is about what is heat pumps. And in a nutshell, heat pumps are just a very efficient way of heating the home through the heat extracted from the outside air with an air source heat pump or ground with a ground source heat pump, and delivered to your radiators and hot water cylinder with the help of electricity. So as some of this energy is actually extracted from external sources, heat pumps are able to deliver around 4 units of heat throughout the year for every unit of electricity that they consume, which would mean that 3 units of that heat is kind of free. In addition to reducing the overall energy used for heating, they can also reduce the customer bills further when combined with the variable tariffs that we've been talking about today, such as the Agile Octopus. And Homely Thermostat is kind of the brains in the background to make sure that the customer doesn't need to run around and turn his heat pump on and off every single time he sees a price dip, So in the background, this is where Homely would take control, and it would try to heat your house during the slightly overheat your house during the cheaper times, and coast through the more expensive periods. Just in terms of how the heat pump works, and I'm not going to go into detail again here, but on the slide at the moment, you can see the reverse refrigeration cycle. It has basically 4 main components, which are the evaporator, compressor, condenser, and the expansion valve. The way that the heat pump works is that the evaporator extracts heat from the collector and transfers it into liquid contained within the evaporator called refrigerant. So this would be your outdoor unit, for example, for an air source heat pump where there's a fan running. The refrigerant starts to boil once it's heated up by the energy from the collector. The gas generated then moves through the compressor, which increases the pressure of the gas, which results in an increase in this temperature, which then the high temperature gas travels to the condenser, which transfers the heat to the heating system. So on this side, you would have your hot water tank and radiators. And then the final step in the process is the expansion valve, which removes the pressure of the liquid, allowing the gas to removing the pressure, allowing the gas to convert back into liquid, and then it goes into the same cycle again. The reason why, as mentioned, why heat pumps are so different from gas boilers is due to their efficiency changing with the outdoor temperatures that they're operating in, and also with the flow temperatures that they're emitting into the radiator side. So on the screen, for example, you can see a COP, which is a coefficient of performance. Coefficient of performance meaning the ratio between the heat produced by the heat pump and the electricity consumption. So COP of, for example, 3 would mean that the 3 units of heat are produced for every unit of electricity that you're using up. On the graph here, you can see a screenshot of the NIBE F2040 8 kilowatt heat pump, showing the coefficient of performance at different flow temperatures. So these lines, the blue 35 degrees, red 45, and green 55. These are the different flow temperatures of the system. Flow temperatures, I think the easiest way to think about it is that it's the water temperature that is going into your radiators. So the higher the temperature that is going into your radiators, the lower the efficiency would be for the heat pump. There's also a change in the efficiency of the heat pump when you have the change in the outdoor temperatures. So as you can see, as the outdoor temperature here, for example, reduces, so if you're moving away from the outdoor temperature of 10 to the outdoor temperature of 0, your coefficient of performance at flow temperature of 55 degrees would drop from 3 to 2. So you would only get 2 units of heat for every unit of electricity that you're consuming instead of 3. Is there any question in terms of this? So as I said, I was going to be very brief for the heat pump side, but this is quite an important concept to understand kind of why the way that we operate is quite different.
Karolis had a question just now from Steve. Steve asks, what percentage of the current housing stock do your studies show are heat pump compatible, and if they can achieve your COP figures?
I wouldn't be able to answer the question. I can come back to, I can look into this because I think that there might be some better people to answer this question in Evergreen, but I wouldn't have the figure to hand.
Yep, no problem.
Sorry.
Yeah, sorry, Carol, you go first.
I was just going to say I think that the question comes from how many houses can actually store this heat. So because the building stock of UK is quite leaky, and I think that there is a lot of work to be done in terms of retrofit to make sure that these houses are more energy efficient before you're kind of putting on the heat pump. There is also the fact that to run the heat pump at lower flow temperatures. So if you're trying to improve the efficiencies of the heat pump, one of the ways to do this is mentioned by reducing the temperature that goes into the radiators. To achieve the same kind of heat transfer, you need to increase the size of them. So just kind of slamming a heat pump on a house with its current infrastructure might not be suitable for a lot of cases, although those improvements are not, there might be some certain improvements that need to be done. Evergreen do have a funding calculator if that is of interest. By putting in some details, you can understand a little bit more about what the costs would be in terms of radiator replacements and that kind of side of things.
Thank you, Karolis. We have a couple of other questions. Can I go through them? Is that okay?
Yeah, sure.
First, from Chris, if you can incorporate your system a variable temperature flow on heat pumps, so when you switch between heat and hot water to maximize the coefficient of performance.
Yes. So the flow temperature of the heating side would be different. Usually, well, it would be different from the flow temperature for the hot water. So that those are two separate things, and there's not really. I don't think that there is much cleverness in there from our side. The Homely system does have a couple of heat pumps where it integrates a little bit better, where we can actually change the flow temperature set points. And this is something that we're doing at the moment, where throughout the day, depending on how the optimization algorithm actually delivers us the optimal temperature profile of the flow temperatures, rather than just the on and off signals. So as an example, you could see that if the price of electricity is very low, let's say 1 pence per kilowatt hour, for example, in the middle of the night, and there's only that one specific period where that electricity price is so low, the flow temperature would be increased to the maximum that it can get to. So if your system has been designed for 45 degrees, your flow temperature set point for the heating side of the house would increase to 45 degrees and the heat pump would turn on. If the price difference, for example, between the two periods would be much lower, so let's say you have 3 pence per kilowatt hour and 3.5 pence per kilowatt hour, it might be more beneficial for your house to be heating at more or less this similar flow temperature, just so that you don't reduce your coefficient of performance too much.
Thank you, Karolis. We have one more question from Joe. Regarding the red and the green line that you have in your graph, we can see that they do intersect around -10 Celsius. If you could provide an explanation on that.
This is quite embarrassing. I've never actually looked beyond the -5. As in, I completely appreciate where the questions come from, but we in terms of the temperatures that we're working here in the UK, I've never actually gone that far out, and I've not looked into that. It will be this will be a more technical explanation on the heat pump side, and this is definitely going to be something that I'll find out now. But yeah, sorry, I wouldn't be able to answer.
I just wonder whether there was a simpler explanation. That was all, Karolis. I mean, if it's all quite technical, don't bother. But my eye was just drawn to the fact they intersected, and I just wondered why. So, but if it's not a simple explanation, don't worry.
I'm not. So actually, I don't know, and it will be more of a technical side of the heat pump. As I said, because we don't operate with those kind of temperatures often here in the UK, we kind of usually look into the area between 0 and 10. I will find out for next session. That will be something that I will definitely have an answer to. Thank you.
Thank you, Karolis. We have a comment, a response from Michael. Michael says that the answer to the above question is twofold: the energy efficiency of the dwelling and the amount of heat transfer surface available. Most dwellings of an EPC rating of C should be suitable depending on radiator and pipe work sizing. I think Michael refers to the very first sorry, to the very first question, what percentage of current housing stock do you study? Michael, would you like to?
That's correct. Yes, that's what I was.
Thanks. So that was a response of Michael to the very first question. What percentage of the current house stock do your studies show the heat pump compatible, that the heat pump are compatible, and can you achieve your coefficient of performance figures? Thank you very much, Michael. Karolis, would you like to continue? We don't have currently any new questions. Thank you.
Sure. Thank you very much, Michael. So now we're moving into the bit about the Homely controls and what is it that we do at Homely. I'll touch upon a couple of other things like the battery integrations and PV. It's just something that we've been working on. I think that it's quite interesting to see all of those different vectors interacting with each other. But just as a brief, so Homely has been designed as a smart thermostat specifically for heat pumps. It was always with the heat pump in mind, and it is to kind of account for those coefficient of performance drops. So when we're modeling the heat pump operation and we're optimizing for the house, the inputs that are going into the algorithms is basically what are your set points. So what is the minimum temperature that you would like to achieve in this dwelling? We then look at the weather forecasts for the next 24 hours. We look at the electricity prices for the next 24 hours, and we try to figure out what is the best scenario for the heat pump to operate, given that we know the information that, for example, if we raise the flow temperatures to higher, we're going to be losing out on the efficiency of the heat pump. And also, if we're going to be running it at a very cold temperatures in the middle of the night, that would also reduce the efficiency of the heat pump. So in addition to that, there's also the learning element of the house. So every house is individually learned in terms of how long it takes for it to heat up and cool down. And that is based on kind of the temperatures outside. We look at the temperatures outside, we look at the temperatures internally, and we fit parameters to identify what is the building profile as a building profile in terms of that particular property. There are quite a few different controls that we do offer. So we do try to cater for different different customers, because we believe that the smart tariff control is really interesting, but there's also the element of we want to make sure that the installers who are installing heat pumps have the ability to monitor them and identify issues even before the customer does. So we don't see it just that Homely is going to be just for the smart tariff. There's also the bit where Homely can be used as a standard thermostat or just the smart thermostat on a fixed tariff, but it provides the installer the ability to track the system performance. So we have standard control, which is kind of works as similar to your rotary dial thermostat. So it only turns on when you want the heat pump to turn on, although when it gets to a certain temperature. So let's say that you had the 20 degrees as a set point. When it starts approaching, the internal temperature starts approaching to 20 degrees, the heat pump would start to reduce the flow temperature that is emitting into the house, so that temperature kind of stays at your optimal temperature. And we're trying to maximize the efficiency at that time, although we're penalizing the household because we're not actually running the heat pump throughout the day, and we're only allowing it to turn on during specific times. Which means that it needs to reach quite high flow temperatures just as it starts up. Smart control. So for fixed tariffs, this is kind of where we would see that the heat pump operates the most efficiently. It would be using the information on the weather forecasts and also on the coefficient of performance to maintain the temperatures that you've set, the minimum temperatures that you've set. We see that very similar to what the weather compensation operation of the heat pump would be, where basically you're trying to compensate for the heat loss of the house rather than trying to work it as a smart thermostat where it just heats up before the times that you need it. And this is all, I'm going to go into a little bit more of that detail because I think that it's quite an important point to raise when you're talking about heat pumps, that they're going to be operating different to boilers. And then there is the smart tariff control, which again, we're looking at this is the smart plus control, where we look at the electricity prices, as well as all those different intricacies of the heat pump, and we're trying to overheat the house and use the house as a bit of a battery to make sure that we don't consume power during the most expensive times. Just to provide a little bit of an intro in terms of other smartness that you can get in the house, we've run some simulations where we included the PV and the battery and the homely, and just kind of comparison of the costs. Before I move into that, just a couple of assumptions. So we did these for a house based in Bristol. We assumed that the heat pump is providing both heating and hot water. The fixed tariff electricity that we assumed in this particular place was 17.745 pence per kilowatt hour. The fixed export rate was 5.5p. And we were modeling a well-insulated house, 2016 build, with a 6 kilowatt heat pump and around 91 square meters area. As mentioned, we did include the ability to take into account PV and battery. So PV installation, we assumed 2.9 kilowatts and the battery capacity of 4.8 kilowatt hours. Moving on to the customer benefits for this kind of control, there is the optimization savings when in smart tariff control mode. So estimate the heat pump running cost for year 2020 using 2020 Agile Octopus prices. If you were to run your heat pump on a fixed tariff, you would have paid around £500. Just by switching to an Agile tariff, you would have paid around £252. And then adding homely on top of that, you would have saved an additional £77. This is just for the heat pump control. It's not considering all the other components in the house. But if you're trying to go into the actual benefits of PV and battery control, and if you're combining all of those different things, this is in this slide, the table over here, you can see this includes all the other house consumption, as well as the heat pump in that dwelling. So for the full house, if you were on a fixed tariff, you would have paid £1,043 for all your electrical use. If you had a heat pump, PV, and a battery, this would have reduced to 631. If you were to use Agile, that cost would have significantly dropped to 343. And then if you were to add a homely on top of that, that would have been an additional £192 savings. As mentioned, homely there are additional benefits in terms of monitoring diagnostics for the installers, which we believe is the really important part when we're trying to go for this increased uptake of heat pumps in the UK. We need to make sure that those systems are installed correctly and they're performing well. And I'm just going to go through some of the aspects where it becomes quite interesting when we're doing the modeling of the heat pumps. So if we were to assume, for example, that a heat pump would be operated on a standard thermostat, so a rotary dial thermostat that is installed in the property with a set points of 21 degrees between 6 and 10 o'clock at night and 8 and 10 o'clock in the morning. If the heat pump is only allowed to operate during these specific times, and let's say that the flow temperature maximum is set to around 50 degrees, you can see how the coefficient of performance of the heat pump, so it would be around 2.5, just as you reach those flow temperatures of 50. And this is coming back to the points where we're looking at different flow temperatures achieving different efficiencies. And we can see how if it's only allowed to operate during these times, the temperature that you're actually aiming for internally would never be achieved, just because the house loses more heat than you're actually providing it during these times. The smart thermostat would be if you were to, for example, use any other smart thermostat where you would just try to anticipate the set points of your temperature set points throughout the day, so the morning and the evening, and the heat pump would try to heat up just before that time. We can see how the flow temperatures would be slightly lower here, just because the heat pump kind of tries to achieve those temperatures as close as possible. but we can see how for part of that time the heat pump does turn off, just to make sure that it doesn't use the heat during the times when it's not needed. And then, so for example, after your evening peak, you would turn off the heat pump, and then it would only start heating up at the right time before the morning peak to make sure that it has that temperature. Then if you were to go for the kind of fixed tariff control of the heat pump with the smart mode, which is the point at which you're trying to consider those flow temperatures, we can see how the heat pump would actually be operating throughout the day continuously, reaching COPs of 3.6 and even up to 4.3. This increase in the COP is actually dependent on the outdoor temperature that is not plotted on these graphs. But that's why you can see that gradual increase in the COP. And we can see how the flow temperatures are actually trying, the algorithm is trying to keep these flow temperatures fairly low at around 37 and 35 degrees. And the temperature indoors is not really changing that much throughout the day, which is which confirms some of the theory behind the weather compensation curves and heat pumps running the best using the weather compensation. And then if you're moving further from that, so the homely thermostat and the variable tariff, then it becomes even more different. So we can see how throughout the day, now we are raising those flow temperatures slightly higher than what we did with the smart control with a fixed tariff. But we're using that cheaper electricity during the cheap pockets. So over here, for example, as we see that on the bottom graph, I have the agile tariff overlaid with a fixed tariff in that particular region. We can see how the heat pump is actually turning on during those dips of price here, over here, and then just before the morning peak. It also tries to significantly overheat the house during the just before the peak time, so that it can coast through the whole of the 4 till 7 period without actually needing to heat that property. It does mean, although, that your flow temperatures and the efficiency of the heat pump is going to reduce when you're trying to overheat this house during these times. But it's something that we've taken into account, that the cost savings that you can make by avoiding the peak price is sufficiently good for you to reduce the coefficient of performance of the heat pump when operating during the cheaper pockets. Yeah, so that's kind of explaining, going into a little bit more depth in terms of how heat pumps can be controlled. Is there any questions at this point?
Karolis, yes, there are a few questions. Would you like me to go through them?
Sure, that'd be great. Yep.
The very first one is in a previous webinar. This is from Mark. Sorry. In a previous webinar, we spoke that heat pumps compared to gas boilers don't like being frequently turned on and off. Is this considered in the smart thermostat algorithm that you have developed?
So, do you mean the smart control side of things, where it tries to operate with the fixed tariff or the variable tariff? This one.
I suppose that Mark's question is more general, because we do know from experience that it is not always good practice, to switch on and off the air source heat pump, the device, versus the gas boiler that we know that switches on and off quite frequently, and whether this frequent switch on and off of the air source heat pump has been taken into account to your algorithm. Because you have worked in the past, I know that it has been taken into account. But Mark, is that your question? Is it, or is it something else that you would like to?
Yeah, spot on. Thank you. That is correct.
So one thing that I have to be honest, one thing that we haven't looked into is the startup COP of the heat pump. So we have been told that there's a startup COP penalty that we could consider in the future, where you turning the heat pump on and off would actually reduce your COP slightly. We have looked into it briefly, and it didn't seem like it made we've looked into it briefly, and the control frequency at which we send the control is half hourly. So we would never turn on the heat pump more frequently than every half hour. So in terms of the startup COP, we haven't had a chance to look into that because we need to hook up quite a few different things on the heat pump and have a very frequent data in terms of how much the COP actually changes during the startup. In terms of taking into account whether the kind of badness of turning the heat pump on and off, so we do not allow the heat pump to be turned on and off more frequently than half hourly, and this is something where we've spoken to a couple of manufacturers where we were trying to understand whether there could be an issue with turning it on and off at that frequency, and it didn't seem like it was of concern. With the smart implementation, so if only working on smart mode with a fixed tariff, the heat pump, as you can see, does operate just throughout the day continuously. So over here, it's not much of a concern. There's also the point that some heat pumps are variable speed and some heat pumps are fixed speed. So in certain circumstances, the heat pump itself might be turning off and on when it's trying to maintain that flow temperature set point. So in some aspects, sorry, to answer the question, in some aspects we have considered it. So we make sure that basically we don't turn it on and off more frequently than half hourly. In other aspects, there is still a little bit of work in terms of trying to understand that very granular startup COP, which we don't believe that it has a massive effect, but it's something that we will be looking into very soon, just to actually understand whether there is a concern that we should be looking into.
Thanks, Karolis. So I continue to the next question is from Michael. Setting aside the potential advantages of community scale energy storage, what would you suggest the components, which components would you suggest for a resilient and adaptable system for an individual dwelling?
So is the question that if you don't have the community, what could a dwelling do to maximize savings?
So basically, at the moment, for not considering community scale energy storage, what would you suggest that would be the appropriate components for a resilient and adaptable system for individual dwellings? Michael, is that the question?
Yes, that's the question as written.
Excellent. No problem.
Just to understand it better, so is the question that which components would you like to have in a domestic dwelling if you don't have a community, so a community based?
Yeah, if I can kind of set out a scenario, if we take together a kind of set of components, be it a Tesla battery, a phase change thermal storage, a hot water system cylinder of a given size, it might be larger or smaller depending on how much it's useful to have that. The possibility of a smart control system and the heat pump. What would you say for a resilient system? In other words, one which we could invest in with some confidence that we're not going to regret the decision 10 years down the line. What do you think the components of that system might be?
So it's a very loaded question. There are so many things, so many considerations to take into account. So one of the things that we've started doing is as kind of in this slide, I was trying to point out the kind of heat pump plus PV, and heat pump PV plus a battery. So kind of we can look backwards in time, and we can see that for this specific dwelling. So if we know how long it takes for this house to heat up and cool down, if we know the other consumption of the house, how much they could have actually saved by putting in these different technologies in there. And this simulator, we're working on it internally to kind of try to make it more accessible for others. so that you could potentially type in some of the information, and it could give you a better understanding of how the savings will look like. It's really difficult to say where we're going to be in terms of energy costs in the future, and how they're going to be varying throughout the day, and which of these components we'll need to include, and that's where we're working on that kind of understanding. For example, the thermal store, is that a good alternative, for example, to a battery? How much benefit does it bring, the battery combined with a heat pump? I'm not sure whether I can answer exactly what components there are. It's going to be very much dependent on, from the heat pump perspective, it'll be very much dependent on how efficient is your home, I think, because then you'll have the trade-off kind of whether it's more suitable for you to store that heat in the buffer tank or in the battery to use it at a later point. And then you're looking into the different components in there, such as the PV, the battery, and the EV. I can explain the different components and how they would affect it, but I don't think that I can say which what are the actual component that golden component basket.
Thanks, Carolus. Don't struggle any further.
Thank you.
I had to admit to posing the question before you put that slide up, and that slide does obviously represent an attempt to address the question, but it is an impossible question.
Yeah.
Another question from Michael. If you have modeled a combination of heating and hot water against a variable tariff regime?
Heating and hot water against the variable tariff. Sorry, so this slide over here, when I was, so all of these simulations, when you see these spikes in the flow temperature, these are actually heating up the hot water tank. So all the figures that I've used here are for both heating and hot water. Was that the question?
Yeah, I didn't appreciate that at the time. Yes, so yeah, that answers the question. Although it does raise other interesting questions, and that is whether there might be a smart regime in which you adjusted the condensing temperature of your heat pump, if it allows it, to maximize the heating of a hot water system at certain times, whilst at the same time not compromising the COP performance at other times when the heat pump is devoted to its heating function.
Yes, so this is the way that the optimization worked when I was doing these slides is that the actual set point that we were setting for the flow temperature when it was working in hot water mode was 55. The current version of the algorithm does take into account kind of what is the optimal temperature set point for the hot water heating. It's not really the flow set point that we can set on the heating side. It would be just kind of what is the target temperature that we would try to get to for the hot water. So when we're doing it with some of the heat pump manufacturers, what we can do is we can adjust, as mentioned, the flow temperature. So if you had, for example, a Samsung heat pump that is controlled with a homely thermostat, you would see that your flow temperatures of the heat pump throughout the day are changing, the same as on this graph. You can see how they're varying from 38, for example, to 35. And then when it goes into the hot water heating, it would have a set point of that hot water. So, for example, charging it to 55 degrees. If you have a requirement of 50 degrees hot water tank temperature at 7 o'clock in the morning, it could be that we can overheat that tank to 53 degrees or 54 degrees to make sure that we still have some residual heat throughout the day. And that is something that in the new optimization is actually taken into account. What is that optimal set point of the hot water, which I think addresses the thing that you've mentioned, Michael?
Yes, thank you, Carolus.
Also, I would like to comment here, Michael, regarding your first question about the additional components or devices for the domestic sector for energy and cost saving. Matt Roderick, who is the speaker after the break, is going to cover this area of integrated solution for cost and energy saving for the domestic sector. I continue to the next question, Karolis, from Joe, whether your model that you presented to us assumes no occupancy during the day. If so, would the same benefits occur if the house was occupied during the day, which is particularly relevant now that many people are working from home? So basically whether your model has taken into account the occupancy factor. Thank you.
In terms of the occupancy factor, so there are a couple of components in there. Occupancy factor in terms of that there is residual heat being emitted into the house, such as every person, for example, emits a certain amount of heat into the house. That is something that is not taken into account. So when we learn the house, we assume that it is just the house and there's no kind of external factors that are affecting it. In terms of occupancy for the set points, the way that this was optimized is we were assuming the profile of the minimum temperature of 21 degrees between 6 and 10 o'clock in the evening and 8 and 10 o'clock in the morning. It does change, it would change slightly if you were trying to achieve kind of those temperatures throughout the day. If you were to look at for example, the standard thermostat. So if you had the set point from the morning all the way to the evening, because of the way that we've changed the way that we work, the standard mode would have actually managed to achieve those temperatures, and it would kind of maintain that 21 degrees throughout the day. For the smart thermostats, other smart thermostats, they would have also heated a little bit more throughout the day to kind of maintain the at least 21 degrees. But as you can see, when you go into the smart mode with a fixed tariff, for example, the temperature is actually maintained above 21 degrees throughout the day, just because it's the algorithm sees that as the most optimal solution to make sure that we have the minimal flow temperatures to compensate for the heat that we're losing out of the house. So if you were to, for example, have that set point of 21 degrees between 8 and 10, I wouldn't think that this result would change significantly, although this is not that particular case. But I wouldn't say that I wouldn't think that it would change significantly. In terms of the variable tariff as well, we can see how the house is never below the 21 degree set point. So even if you were in the house and you had the minimum set point of 21 degrees, the actual profile of the heating would not have changed significantly, unless you didn't like the house being slightly warmer than your minimum temperature. So one of the other components that we ask the customers is, what is your flexibility? So assuming that, for example, you want the house to be at least 21 degrees throughout the day, what is the maximum that you will allow it to be if we were to save you money? So are you comfortable with 21.5, for example? So during the period here, just before 4 p.m., would you be okay for the house to reach the temperature of 21.5 degrees? Or would you be comfortable with 22 even if it would save you even more money? And that would be another consideration when we're looking at the occupancy throughout the day. But in terms of if it is just the minimum temperature for the kind of smart control and smart tariff control, I don't think that those profiles would change.
Thank you, Karolis. Also, I think your response was very thorough, but also from another angle, the same issue will be approached by Matt Roderick in his wonderful section, which will be after the break. But thank you very much. Also have a comment from Tom, who says that it was very satisfying seeing the details of this optimization algorithms in practice, and thanks you very much. Karolis, would you like to continue to the next?
So I think that way, in terms of this session length, I think that I do have another section, which I wasn't sure whether we're going to get into. This was the first trial that we did at the Smart Meters Lab.
I think if you would like to briefly present, that would be fine, but because we are going towards our break, so if you would like to briefly describe what you did with us, that would be nice. And then we can go to the break.
So I'll just very quickly then try to screen. There we go. So can we see this?
Yes.
Screen. So this was at the very beginning of Homely, and Smart Meters Lab has been very, very helpful in the way in where we've gotten with Homely, just because when we started off, it was really difficult to convince people that this is actually this was around 3 years ago now, and it was really difficult to go into presentations where you didn't have the data that it was actually supporting the claims that you were making in terms of savings. And this is where Smart Meters Lab has been instrumental in helping us. So what we were trying actually to do in the Smart Meters Lab is to show that there's a potential for savings, and we present here the 20% savings whilst using Homely controls and variable electricity tariffs. So the test has been done in the Smart Meters Lab using the NIBE heat pump and a single drum control, which is slightly different to kind of controlled conditions that you could achieve in the energy house, but it was a good kind of starting point. Again, we consumed a very kind of original scenario, which was the kind of 21 degrees as a set point. So if you were to work a heat pump on a weather compensation curve, which was the kind of default setting on the NIBE unit that we were using, how would that compare to the smart control when using the Homely and Octopus Agile, where you had just the morning kind of set point of 21 degrees and the evening set point of 21 degrees. Limitations, so the testing has not been done under controlled conditions, but to show that the results were still applicable, we actually penalized the Homely controls day. So when we were choosing the temperatures of the outside for the Homely controls day, we used a much colder day to make sure that if it was like for like, you should have paid more for the electricity used when heating using Homely on this particular day compared to the original kind of approach. And then with the original controls, so this is the temperature profile, achieved the internal temperature profile that we've seen when the NIBE control has been running on the weather compensation. We can see how the heat pump just kind of turns on and off, kind of trying to maintain that internal temperature at 21 degrees. It doesn't have an internal temperature sensor, so it was purely working on the weather compensation curve, and the positioning of the weather outdoor temperature sensor was actually affecting some of the accuracy in terms of what the internal temperature actually can achieve compared to what indoor temperature is. So we can see for a lot of this, the internal temperature was much lower than the 21 degree set point that we've set it up to be. And then using the Homely controls, we use the same heat pump, but we were operating it during the cheaper times using the Octopus Agile rate available on that particular day. And we can see how the actual power consumption increased slightly during the times when we were turning it on. How the heat pump was overheated throughout the day to achieve the 21 degrees in the evening, we got the temperature to actually 21.8 mid-afternoon, just to make sure that we can jump through the 4 till 7 period and kind of still maintain your set points. And as mentioned, this was on a much colder day, so you would expect the heat pump power consumption to be slightly higher. Just as a conclusion, so what we've seen from that initial trial is that with the original heating control and the cost of electricity, it would have been £1.57. With Homely heating control on a colder day, it was £1.26, which was a strong backing for what we were going to with when we're going to people and kind of explaining what we're actually doing. This has really helped because there was something that was we've done a physical example of how it could work, and it does work, which I have to thank Giannis and the team, Smart Meters Lab.
Thank you very much, Karolis. It has been a pleasure working with you all these years in such an innovative product. Can I very quickly before we go to the break, I have a question from Michael. The dilemma of using fabric storage is that the lowest cost electricity is at night when we are tucked up under our duvets. We don't want our bedrooms heated to 23 Celsius just to ensure that the kitchen is warm at 8 a.m. A well-insulated dwelling should be able to coast through the night without the bedroom becoming uncomfortably cool. This is where thermal storage capable of a quick preheat before the heat pump takes over might be a good option. That was a comment from Mike. Thank you, Michael. I suggest to go for a 10-minute break and come back at 14:35. 14:35, sorry, if that's okay. And we will continue after the break with Matt Roderick and Wonderwall for the products and services for the smart home ecosystem. See you all in 10 minutes. Karolis, thank you very, very much for your very, very interesting presentation.
Thank you very much, Johannes. Thank you, everyone.
Thank you. See you in 10 minutes.
See you. Bye.
Hello again. We are starting the second part of today's session, and in the third talk, which will be delivered, our speaker will be Matt Roderick, and the title is Products and Services for the Smart Home Ecosystem. A few words about Matt. Matt Matt was founding executive of the digitization of Great Britain's last analog industry, smart meter rollout, and CTO of Vodafone's revolutionary M-Pesa service, mobile banking. Now, Matt focuses on enabling businesses to take advantage of wider energy transformation, on how we all consume, store, and generate energy. Also, Matt is founder and CEO of the Energy Data Platform and CTO of Wonderwall Energy. Matt, before you start, may I ask you to say a few things about the Energy Platform, because we had some questions in one of the previous talks that some of the people who participate in this workshop would be interested on accessing smart metering data, and the energy platform that you have developed would be very, very useful. Thank you very much, Matt.
Thanks, Ernest. Yeah, off the back of that, hi guys, hi everybody. Off the back of that, what I've actually done is tweak my slideshow a little bit for this afternoon and added a couple of slides on energy data. So let me just share that where I can find, where's the share button gone? Here we go. So hopefully guys, you can see that slideshow. So as I mentioned, I've tweaked the slide set. I was just going to talk about Wonderwall, but now I'll be talking about a couple of slides on energy data first. So hopefully this covers off some of the questions earlier on. So energy data, what is it? It's you see the strap line there. It's about changing the energy industry or data within the energy industry from blockbusters to Netflix. As Nigel beginning of the afternoon, it's a very analog industry, and it's starting to transform to use digital, to use data to really make it more efficient and effective. And energy data is one of those platforms that have come into the industry to make it easy to access smart meter data. And, here we go. So it's a very simple process. It sits in the cloud. Its primary customer base is for businesses. It's a B2B service to enable businesses to access data from domestic and non-domestic smart meters from around the country. Very simple. Sign up to the platform, as all good cloud services. Sign up to the platform in a couple of minutes. Very simple and easy to use APIs, and you'll see an example of that in a later slide. You can launch within, actually our faster customers launched within 36 hours of signing up to the platform. So it really is that easy, and you can access up to 17 million meters, and that's growing on a daily basis as part of the national meter rollout program. The sign up for consumers is relatively straightforward, and if you click on the link that you'll see at the end slide of the energy data section, you'll be able to sign up your own meter for free to the platform and download your own data from your smart meter. No consumer access device required, no specialist equipment, no comms connection, nothing particularly complicated. It's just a straightforward log into the website, type your details in, and away you go. We'll collect the data from your meter for you and provide it to you through the customer portal or through the API if you're technically inclined. Very similar to PayPal if you think of it that way. What you'll need is your MPAN. Hopefully you all know what an MPAN is. It's your meter point number that's on your bill, 13-digit code, and your in-home display. So here's my in-home display. Flip it over on the bottom, you'll see You probably can't see because my camera doesn't focus, but you'll see a long digit, as you can see on the screen. Type those in without the hashes, the hashes in between, and that's agreed to the terms and conditions, and that's it. We'll collect your data and we'll give it to you to download. The consumer portal, as I mentioned, it's designed as a B2B business. So as other businesses come on board, they will request access to your data over and above the service. You might choose to sign up with us directly. You'll be able to see who has access to your data. You'll be able to withdraw consent from that data, and download your own data. So fully GDPR compliant, gives you complete control of who sees your data and when and what they see. And obviously, sorry, I just say obviously, and every time you share data with a new business, we request explicit consent to be shared. So we'll never share your data with businesses off the back of the T's and C's. You agree with us? Each time a new business comes on board and wants access to your data, we request your explicit consent to share that data, and you can withdraw them individually and independently as well through the customer portal. API looks like this, very simple. JSON RESTful, if you're familiar with that. You give it an MPAN, you give it electricity, gas is also available. You ask for consumption. Generation is also available. If you have solar panels, export into the grid. You give it a start date, give it an end date. You request half-hour granularity, daily granularity is also available. And the data comes back, looks a bit like this. You don't have to use the API. You can download a spreadsheet with all your data from the customer portal and draw graphs to your heart's content. But as I keep on mentioning, the service is designed for businesses to consume. We've added the direct consumer service because there's a lot of individuals out there, let's call them prosumers, who want to see their own data, and energy suppliers are not forthcoming with that data, even though they're legally obliged to share that data. They're not forthcoming with sharing that data. So we provide an independent route. We access all smart meters, all energy suppliers, and all the data that exists within that meter, because in reality, the data that sits within your smart meter, you are the legal owner of that data, and you can do what you want with that data. So that's it from an energy data perspective. Click on the link there to sign up. If you just go to the website data.energyn3rgy.com and click sign up there, that's the business sign up. Click the I'm the consumer link, and what I'll do actually is let me share. Where's share? Let me stop sharing this and just show you the website so you can see it more easily. So this is the website, data.energy.com. Clicking sign up there would sign you up as a business customer. If you click sign up here as a consumer, you type your MPAN in, you type your serial number for the IHD in, and then that's it. The process is complete. So feel free, the consumer sign up is free. In terms of the data that get back, I've just downloaded the last 3 months, I think, of half-hourly data through the API. This is my meter under my stairs, downstairs here. And as you can see, this is not a JSON output. This is a CSV output. You can see it there. We also support CSV to make it easy. And you can see the sort of shape of my consumption over the last 3 months. I'm in a relatively small property, so that isn't high, and I'm quite conscious of my energy use. So it's relatively low throughout the days. Anyway, you get the idea there. That was just a quick flash through the energy data platform. Are there any questions in relationship to that? Anything you'd like me to repeat or cover?
Matt, I cannot see any questions, so if you would like to continue with the Wonderwall part, of course, if you have any questions, we will ask them to you during the session that you are.
Yeah, absolutely. Or at the end of the session,
Yeah.
ask questions on either business or either service. That's fine.
Thank you very
Okay,
much.
excellent. So let me share my screen for the Wonderwall section. There we go. Move that out of the way so I can see it properly. So this Wonderwall provides, in some senses, quite a similar sort of service and system to Homely and the Corellis presentation earlier, but in a slightly different way. Well, quite in some areas, in quite a significantly different way, and hopefully that will become clear. Wonderwall was founded about 7-8 years ago as a home automation company. So we built light switches. We designed and built a light switch. Again, upside down. There's the light switch. You can see in my little video stream. Fits into a standard light switch back box. It has a mini computer in there with lots of sensors, and I'll discuss that. And basically, the principle of Wonderwall was to create a smart home using the light switches, using the array of sensors in the light switch to control your home and make your home better. About 2 years ago, we introduced the energy service within that, and that's the main thing that we'll talk about this afternoon. But we'll also discuss briefly some of the features of functionality within the light switches as well. So let's get into that. So Wonderwall's mission now is really focused on changing the profile of energy use within the home, achieving a net zero home individually without massive change, without significantly, completely transforming the fabric of your building and completely changing the behavior of the occupants. The system works on digital and data and automates many of the assets within the home to really work around the occupants and understand how the home is occupied and achieve that outcome. The heart of the system is the light switch, the switch I just showed you. So each light switch has 13 different sensors in there. It covers temperature, humidity, power consumption, motion detection, luminosity. It has a microphone, it has a speaker. It switches the lights on and off as well by touching it. But it's really through that deployment of the light switch, the Wonderwall light switch, it starts to build up a very clear and concise picture of not only how that home heats up and cools down, but how each individual room heats up and cools down, how each individual rooms are occupied, when they're occupied, what's the sunlight or the lighting behavior within that room. All data points, an enormous amount of data points to drive understanding of the performance of your home, of the domestic property. Typical homes have somewhere between 10 and 12 light switches. So you deploy 10 or 12 light switches within the home. That's 200 sensors, 250 sensors scattered across the home, really starting to build an incredibly precise and detailed picture of how your home performs, and not only how your home performs, but also how you use your home. And we use that data for many things, all dedicated around reducing your energy consumption and reducing your energy bill. So ultimately, there's somewhere between 20 and 25,000 data points a day that Wonderwall collects. I have a data landscape document I can share, and if we've got time, we'll go into this, of what those data points are. But ultimately, it's clear understanding of how each room performs. I mentioned temperature, humidity, motion detection, and so on and so forth, but also how the home performs, how much energy does it consume, the weather forecast. Wonderwall includes solar generation and battery storage, So data points on how well does the solar panels on your home perform given the weather conditions within your area. So all of this data is pulled together. Tariff data is also collected. So you need a smart meter for this service. We collect data from the smart meter, collect consumption data, collect generation data, collect tariff data. So it works with tariffs, as mentioned this afternoon, such as Wonderwall Energy, such as Octopus Energy, Agile's tariff, but it also works with any other flat rate or time of use tariff, economy 7, economy 10, EV charging tariffs, any tariff that's out there. Wonderwall works with, because we collect that tariff from the smart meter and we use that to decide when to take energy from the grid, when to take energy from the battery, when to store energy in the thermal store, or when to take energy from the solar panels. All that data is driven into our AI engine, and that AI engine makes the decisions about how to optimize that property. Give you an example. So traditional heating systems will come on at, let's say, 6 a.m., warm your property up, every single room in your home, knock off at 8 a.m. when you go to work, assuming we all get back to work in an office at some point soon. But that's what a traditional heating system would use. What you might do as an occupant is wake up at 7 a.m., get out of bed, spend half an hour in the bathroom, pop into the kitchen for a cup of coffee, and then dash out the door. So the question is, why do we spend so much energy heating every single room in the home for that 2-3 hour period when you only use 3 rooms for a few minutes each, 30 minutes each, 20 minutes, whatever it might be? Why not just heat those rooms when they're required to be heated rather than just heat up the entire home? And that's what Wonderwall does. That's what Wonderwall focuses on, is selectively heating homes when they need to be heated rather than consuming energy to heat the entire home up. There's a secondary point to that in the area of retrofit. So we've had some discussions this afternoon around how many properties are suitable for low temperature heating, such as heat pumps, because the speed in which a heat pump can heat a property is directly affected by how quickly that property loses heat. But if you don't actually heat the entire property, then you're not going to lose any heat from that property. The heat doesn't go straight out the door. So if you selectively heat rooms, selectively heat them at the time that they're required to be heated, then there's far less energy to be drained through the walls or the windows or the roof of that property, and hence saving significant amounts of energy and significant amounts of money. Some of the key principles Wonderwall drives in its artificial intelligence, the data crunching and decision making of the back office platform. It's firstly and foremost, it's about minimizing energy consumption. It's about not heating those empty rooms or not heating the home. So for instance, Wonderwall drives works in tandem with a smartphone app, and that smartphone app tracks the location of the occupant, tracks your location. So if it discovers that you want the heating schedule to come on at 6 p.m., you want your home, your living room to be at 21 degrees at 6 p.m., but it also discovers that you've left the office and you've gone down the pub for a couple of hours, then we don't heat your living room. We switch that off. We disable that function. We override the behavior, and your living room stays closed because you're not there. You're not there to enjoy that heat. So why bother expending it and using that money? The same principle applies with hot water tanks. So as part of the whole Wonderwall system, hot water tank, 150 to 250 liters, standard hot water tank. But it's an intelligent hot water tank. We can heat 20 liters, 30 liters, 40 liters, 100 liters of water, depending on your consumption profile. If you typically use 40 liters of water a day, then we will only heat 40 liters of water a day. Why expand energy heating 200 liters when you only ever use 40 liters? So that's another principle that's applied through the system. The second sort of priority for Wonderwall is maximizing free solar energy. So a typical Wonderwall deployment takes about 4 to 5 kilowatts of solar on the property's roof, and we maximize that. So if we've got time later on, I'll show you a typical winter behavior and summer behavior of a Wonderwall house. But basically put, if the weather forecast for tomorrow is sunny, then we'll not charge the batteries from the grid overnight, we'll not heat the water in the tank from the grid overnight, and we'll use solar energy to run that home and heat that water and charge that battery within that home during the day, because solar energy is free, where grid energy, even at the cheapest times of day, is still 3 or 4 pence a kilowatt hour. When the weather forecast is variable, like it was today, then the Wonderwall system will make a decision based on historic solar generation of your property that it's learnt since the system was installed, based on grid prices. We'll potentially take that energy from the grid at 3 a.m., 4 a.m., 6 a.m., whenever the cheapest time is, to charge those batteries and to heat those hot water tanks to the sufficient level required for your consumption throughout that day. And we'll repeat that every day, learning every day your behaviors, learning every day what your energy needs are, and optimizing the system to do that. I already mentioned it, but minimizing grid cost. There's no point in doing all those things, but then taking energy from the grid when it's 30 pence a kilowatt hour. So we'll take it when it's the cheapest possible. Typically that can be as low as 0 or even minus figures on occasion, but more often it's 3 to 4 pence a kilowatt hour, those very lowest periods. But it's variable. Again, this is using the Octopus Agile tariff, which tracks wholesale prices. We can use any other tariff as well. So a typical EV tariff will sell you energy at 4 or 5 pence a kilowatt hour between the hours of midnight and 5 a.m. If that's the tariff you're on, then we'll use those hours to take energy from the grid and avoid taking energy from the grid at all other times. And finally, there is a strong correlation between grid energy prices, at least from a wholesale perspective, and carbon content of that energy. So by adjusting the system to minimize costs, we're also adjusting the system to minimize carbon. And this is consequential carbon that is generated from the energy network, not carbon generated by the home, because the Wonderwall system is completely carbon free. It's 100% electric, which has its own benefits and values. This shows a very complicated slide, giving some examples of different energy tariffs and different times of day. So the white line in the middle is, if you're on a flat rate tariff, this is what you pay all day, every day, 15, 16 pence a kilowatt hour. If you're on economy 10 is the grey tariff. If you're on economy 7, it's the yellow tariff. If you're on something like Optical Agile, that's the incredibly wavy and variable purple tariff. And then there's some EV tariffs coming to light, which seemed like a pretty good value in terms of a very low cost price overnight, and then a relatively low cost price during the day. But again, the system will learn your behavior, and ultimately we're hoping to recommend tariffs for an occupant, a home to take based on not just the performance of your home, but the behavior of the occupants of your home as well. So that's working for a bit, but in principle at the moment, we recommend our customers take the Octopus Agile tariff, and we track that because that's the most complicated one, and that's the system that achieves the greatest optimization. So what's actually in our Wonderwall system? I mentioned the light switch, 13 different sensors. It's actually got Alexa built into the light switch as well. And before I started this presentation, I pressed the mute button on my Alexa, so it's not going to start talking to me like it normally does. But it's got Alexa built in, so you can do anything with a Wonderwall light switch that you can do with a traditional Alexa. with a traditional Amazon Echo. With one difference, we implemented a push to talk feature, so it doesn't listen to you permanently. You press the button, you press the W, and then it starts listening to you, can talk to it, because we had quite a lot of feedback with concerns around that. So the default configuration is it doesn't listen, you press to talk. But you can order pizzas, you can order Ubers, you can do everything. Play Sudoku, you can do everything you can on a traditional Amazon Alexa, plus control your home as well. The second element of the one-to-wall solution, and I've sort of touched upon this in the presentation so far, it's around intelligent gas-free heating. So we have the hot water tank, an intelligent hot water tank. It can heat a variable amount of water, and also when you draw off that hot water, the tank doesn't mix. It's got a specialist diffuser in the bottom, and the tank doesn't mix to create a tank full of lukewarm water that you have to reheat. But the boundary between hot and cold remains relatively solid within an inch or two within the tank. So if you've heated 50 liters and you draw 20 liters off, you still have 30 liters of hot water in the top of the tank, where traditional tanks would just create 200 liters of lukewarm water that before you want to use it again, you have to heat the entire tank again. So we've avoided all of that. From a space heating perspective, our preferred solution is infrared panels. And that's because the infrared panels are incredibly granular in control, which matches our control system. And also we can apply heat individually to specific rooms. So we can apply heat for 5 minutes into a room, 1 hour into a room, individually, depending on the occupancy and preferences and the learned preferences, as well as the expressed preferences of the occupants and how they move and use their home. So the last piece of modeling we did in this area, in a typical one-to-wall home, as compared to the SAP standard of heating the entire home to the appropriate temperature throughout the week, takes I think around 77 hours of application of heat. We typically expand about 36 hours of heat. Might be 34, I can't quite remember the figures now, but it's between 34 and 36 hours of heat. So drastically reducing the amount of energy being consumed by the heating system, and the same principle applied to the hot water system by drastically reducing the consumption of energy in that. The final part of the one-to-wall solution is solar and battery storage. So if you've drastically reduced your energy consumption, and we typically reduce the energy consumption for a property by about 50%, using intelligent hot water systems, using intelligent space heating solutions, then that remaining 50% can come largely from solar generation. Putting 4 to 5 kilowatts on a roof will typically support an entire property throughout that year, so net zero, achieving net zero in effect. Obviously, solar generation is created during the day and the sunny days, and mostly during the winter. So we use the battery to store that. The other interesting side effect that we found as a result of the one-to-wall solution is through a combination of using flat rate export tariffs. Carolus mentioned the 5.5 pence per kilowatt hour to export excess energy, and a combination of the agile tariff, where we typically buy energy from the grid at 4 to 5 pence a kilowatt hour. That ultimately achieves a seasonal storage capability from an economic perspective, at least for that property. So during the summer, when there's enormous amounts of solar generation and you get paid 5.5 pence a kilowatt hour for that excess solar generation after the hot water tank, after the battery is full, that gets pushed out to the grid at 5.5 pence a kilowatt hour. Then in winter, we start consuming typically wind generated energy at those 3 a.m., 4 a.m., charging the battery, heating the hot water tank. We're again paying 4 to 5 pence a kilowatt hour. achieving, economically perspective at least, seasonal storage in a Wonderwall home. I'm sure the questions are mounting up in that. Hopefully we'll get to in a second now. Finally, what does that mean? So a home automation solution will integrate with a gas boiler. It isn't as efficient because you can't control room by room with a gas boiler. You might be able to control zone by zone, upstairs and downstairs, but typically it's a whole house thing. So we can achieve through switching the gas boiler on and off, taking the temperature sensor from the room you're in rather than where the thermostat is, because the light switch has a temperature sensor. It knows which room you're in. It knows what the temperature in that room is, and therefore that will be the target temperature to drive the typically gas combi boiler. And overriding behaviors like there's nobody in the house, let's not heat the house, even though the schedule says it should be heated, we can achieve about a 20% energy savings. By introducing the intelligent gas-free, that intelligent hot water tank, that room by room granularity of application of space heating, we can halve the energy consumption for that home. And then through the application of solar battery storage and that intelligent use of solar, of generation storage, and then economic delivery within the house, we can achieve about a 90% savings. Our first customer deployment was in April of last year. So they've been running for about 13 months now. Actually in East Manchester, in Gorton. They were paying, I think it was around about £20 a month on their energy bill. And when we looked at it in April, they were £230 in credit. So it's not a particularly large house. It's a relatively small house, but that sort of achievement was made with the first deployment of a Wonderwall solution. So quite incredible in terms of what it can achieve. I'm not going to go through this in any detail, but from a cost price, we've compared it to gas combi boilers and to a heat pump. And just to bear in mind, the Wonderwall solution includes I think that price is about 4.5 kilowatts of solar. Actually, it's 5.5 kilowatts of solar, 6.5 kilowatt hour battery, the smart hot water tank, a bunch of panels. I think it's about 8 panels in that 10.5K installation price. Whereas obviously a heat pump includes a heat pump and the radiators required. The other benefit from a Wonderwall is there's no wet system in the house other than the kitchen and the bathroom now. So the potential for leaks is drastically reduced as a result of that. It's all electric. Plumbing becomes incredibly a lot simpler, and no oversized radiators. We're working with many of the leading housing providers, both from a new build and the retrofits perspective. And I hope you'll see more from Wonderwall over the next couple of months as we're making some real large strides within these areas. And we've won a bunch of awards as a result of the different take the different perspective we've taken on net zero and efficiency, the digital first approach to drive a far more efficient model. That includes actually how the home is being used, not just how the shell of the home, the fabric of the home performs on its own. We've created, because of the vast amount of data we collect, we've also created specific services for the social housing sector. So we provide a landlord dashboard. Now, through this landlord dashboard, our customers are now starting to understand the condition, better understanding the condition of their home, better understanding the safeguarding and vulnerable members of society. If a particular property is constantly underheated, then that occupant might be concerned about, it might be think themselves in fuel poverty, even though the Wonderwall system does a lot more. But understanding and being able to educate that tenant and to move that forward. Property vacancies, over occupancies, over amount of excess damp over usage. All this information is provided and shared through the Landlord Dashboard provide. And there's a thousand other things that we can do from the data, and we're hoping to create a bit of a data partner ecosystem where other organizations can start to build services upon the 25,000 data points a day that Wonderwall collect and apply to the heating system. Same principle as energy, though, as I suspect you would ask the question. That data will not be shared with anyone without the explicit consent of the occupant of that premises, whether it's rented or whether it's self-owned. And because of the vast quantities of data, we're continually learning, we're continually understanding different ways and means to optimize the property. So unlike many of the non-digital solutions that are being deployed within homes at the moment, i.e. straight, not homes like systems like the Homely system, but the straight standard basic control heat pumps, they will never change, they will never improve. But with Wonderwall and the digital control and the algorithms we continue to refine and build within our cloud and our light switches, it'll only get better over time. It'll only learn more and behave more. So that's it from me. I think we have about 10 minutes for questions, if my memory works on timing.
Yes, Matt, thank you very much. It was a very, very interesting talk. I have questions both for the energy platform, as you would expect, as well as for the Wonderwall products. Should I start with the energy?
Yeah, why not?
Okay. The first question is from Bell, saying from the response, does the meter connect to the postcode it is located? I think it is the MPAN, isn't it? But
yeah, it's so I could talk about it for a long time, but the energy sector has an appalling address register. That's one of the reasons why when you try to switch suppliers, you either have a relatively clean switch, which takes a couple of weeks, or a nightmare switch that takes months. That's because the address data maintained by the energy sector at large is awful. That's why we just use the MPAN. So if you want to sign up to energy data, dig your bill out, find the MPAN. It's a legal requirement to be had on every bill. You can use the MPRN, the gas meter point name as well. It works just as well. Type it into the system and you can sign up. We will continue to avoid address data while the energy industry continues to have a messy database with regards to address data.
thank you, Matt. I continue to the next question. The next question is from Tim, and is the following. Energy is great for a prosumer, as Matt suggests. Is there an opportunity to pull this data as a group to drive local demand-side response balancing, rather than leave it to the DNOs who seem behind the curve?
Absolutely. Let's answer on two parts. The sort of the wide area smart meter network, and Nigel mentioned this originally, connects or will connect by the end of 2025 about 100 million devices. So it's a very heavily laden network. You cannot get real-time data over that network. It's typically once a day, although we're running pilots at the moment that collect that data every 2 hours, still half-hourly data. That will provide a profile to allow demand-side behaviors to be judged after the effect, and provide a profile to allow demand-side action to be planned in advance, but not to be monitored in real time, if that makes sense. If you want to go down the real-time route, you'll need something like a consumer access device, and you'll need to stream the data independently. But it could absolutely play a part. The core platform, the core business model of the platform is to provide businesses with access to hundreds, thousands, millions of data of smart meters and the data within them. So absolutely can be driven from a community. what is fundamentally essential, and I've said this earlier and I'll repeat it again, the data within the meter is yours. It's owned by the occupant within the home, and therefore the explicit consent of that occupant is required and will always be required.
Thank you, Matt. I continue with the energy-related questions. Next one is from Salma. Can anyone with a SMETS2 smart meter use the energy consumer login, or is it, I can respond to that, is any smart meter, SMETS1, SMETS2? Am I right, Matt? That
Almost, yes. So at the moment, the DCC, which is the organization I used to work for, and the organization at the center of the smart meter network, they directly connect SMETS2 meters. They also are migrating SMETS1 meters across to their infrastructure. So we have access to all of those migrated meters and all the SMETS2 meters. We also have direct access to the secure, and Nigel showed a picture of secure SMETS1 meters. We also have direct access directly through secure, through all of those, about 7 million secure meters. What we don't have access to today, and in reality nobody has access to today, is the meters British Gas installed about 7 years ago, because they're not migrated to the DCC and they refuse to allow any third-party access to their metering infrastructure. So they're not available yet, but they should become online over the next couple of years.
Thank you very much, Matt. Now I'm going through the questions which are related with Wonderwall. Yeah, first one from Michael. Can the Wonderwall algorithms be reverse engineered so as to allow retrofit strategies to be explored and system components to be sized by simulation?
That's not something we've done as of yet, because it's difficult to simulate the 20,000 data points a day. So we've really built, optimized, improved based on pilot homes. That's not to say that different things could be done. So some of the deployments we're doing is just the light switches, for example, that draw the monitoring. So light switches combined with data from the smart meters starts to build a picture of how that property is used, with existing heating systems, with existing combi boilers, etc. Through that model, we can then understand the occupancy of that property, the thermodynamics of that property, and start to work out a model of what's the best next step for that property. This is quite important from a social housing perspective, because they will not replace a gas boiler that they installed last year. They want 10 years, at least 10 years out of their gas combi boilers. So Wonderwall has to be a modular solution from that perspective. So I guess yes and no is the answer to that.
Okay, thank you, Matt. I continue with the next question. Is the Wonderwall tank akin to the Mixergy stratified solutions?
The Wonderwall tank is very, very similar to the Mixergy tank. That's about all I can say with that, but hopefully you get the idea of what I'm saying.
Okay. Next one by Tim again. With a wet heating system, could there be an Wonderwall link from the switch to an intelligent thermostat on a radiator?
That's something we've actually been exploring for about 3 years now. The problem we've found is smart TRVs are inherently unreliable. The heat through the radiators affect battery life, and basically you end up wandering around at least twice a year swapping batteries out, and they all fail at different times, and it becomes a bit of a nightmare for the occupant. That's another reason why we went with the direct connected infrared panels, and we use a little relay to switch them on and off. Very simple solutions. Infrared panels last 35, 40 years in many scenarios, and they don't leak water everywhere. And you don't have batteries to change either. So yes, in theory, yes, but we still haven't found a TRV valve that is less trouble than they're worth, if that makes sense.
Yep. Thank you very much, Matt. I continue. A question from Michael. Is it reasonable to assume that PV panels will continue to be able to export at 5.5 pence per kilowatt hour in the medium to longer term as a renewable capacity builds up, particularly from wind turbines to meet winter demand? The demand and therefore market for surplus PV output in the summer months will all but disappear.
That's the $5 million question. You know, what's going to happen with energy prices? There are so many that state energy, because of the amount of renewable in the system, electricity prices will fall through the floor. There are others saying that because of the amount of renewable energy in the system and the cost of upgrading the networks and the cost of storing that energy, grid energy prices will go through the roof. All I can say is over the last 12 years or so, energy prices, the average domestic energy bill has gone from about £400 to about £1,300 a year, and I don't expect that to change. So that's from an import perspective. That's from a cost perspective. What will happen with export? I think the flat rate tariffs for export will reduce. 5.5 pence is probably unsustainable. The far more interesting model for me is, why do we have to sell that exported kilowatt back to a supplier who then sells that kilowatt for 16 pence to your neighbor? Why are they making a 300% markup on, or 200% markup on that exported energy when naturally it flows out to your meter, down the road to your neighbor, and potentially into their house, and the energy supplier makes a 200% markup on that? Having multiple homes in a geography working together and sharing that excess energy, so going into other people's hot water tanks, going into other people's space heating, going into your neighbor's battery, is absolutely where we need to get to. Unfortunately, the regulatory requirement is not there yet to support those sorts of models. So I hope it'll be there in time for before the 5.5 pence starts dropping too far, but time will tell on that.
Thank you very much, Matt. We continue to the next question from Shalma. Shalma asks whether Wonderwall interfaces with other products like Nest.
So not at the moment. Nest is, I've got another slide that I didn't show today, which was a sort of competitive analysis. We are unaware of any one system on the market that competes with all the things Wonderwall does. There's competition in the smart thermostat space, there's competition in the battery storage space, there's competition in the domestic heating and hot water space, but there's nothing today in the market that draws it all together and provides a holistic solution. The argument I normally take is, if you want an EV, you go out and buy a Nissan or a Tesla. You don't go out and buy a wheel from one organization, a battery from another organization, a chassis from somebody else, and try and build it yourself. So why are we trying to do that with homes? Just get one system that works together, all the components talk to each other and work together, and you get the results.
Thank you very much, Matt. I continue with the last question for today, for your session. From Stuart. Stuart says that there was an old-fashioned opinion that it was good to heat empty rooms as well, so as to keep the fabric warm and to drive off damp. What is your opinion on that? Completely agree. If there's damp, if you've got a humidity sensor in every room, then you'll know if there's damp and you can heat that, and that's exactly what we do. If we see humidity build up within the room, we apply the heating to burn that off. If there's a constant humidity issue, then we'll report to the occupant or the landlord, depending on the ownership, to say there's a humidity problem, potential damp problem, time to sort something out.
I guess the one other thing I wanted to mention here, as I've got a direct message from another individual, is around the relationship with Wonderwall and SAP. Wonderwall, and if any of you guys have been working and understanding how SAP work, SAP is an incredibly blunt tool that doesn't really understand data or dynamic or occupancy or room by room or any of those things. And it takes years for it to catch up. So we're driving a behavior in domestic energy use that is very, very difficult to measure within SAP at the moment. And as a result, even though we drop bills through the floor, we drop energy consumption through the floor, the way it's measured within SAP only gives us a marginal improvement. But that's changing. The next version of SAP will recognize a little bit more. The version of that will recognize a bit more again. But I suspect SAP will never be able to keep up with the innovation within the market in general, let alone what Wonderwall's doing.
Yeah. Matt, thank you very, very much for your very, very interesting talk. I don't think there are any more questions. I'm sure that the participants could email you if they have any further questions, either for the energy platform or for the Wonderwall. Thank you very much. And after Matt, we continue with our last talk for today, entitled the Home Energy Management System, HEMS, Introduction to the Connecta X platform. The speaker is Jose Figueiredo, if I have pronounced this correctly. Jose is a software engineer with a master's in software and computer engineering. He has participated actively in the development and launch of broadband IoT technologies, and more recently at Critical Software, Jose has led several R&D projects for the UK's smart metering implementation program, of which the Connecta X project is part of. Jose, to you. Thank you very much.
Thank you. Just give me a moment. Just put a PowerPoint. Can you see the presentation?
Yes, thank you.
Okay. Hello everyone, I am José Figueiredo from Critical Software, and I would like to welcome you to the Connecta X presentation. Connecta X is a critical software R&D project in partnership with the University of Coimbra. Presently, in many smart homes, we have two distinct sets of smart technologies. One set of smart home technologies is all the systems that are monitored and controlled by the home user, such as temperature and humidity sensors, lighting and energy socket controls, intrusion and emergency sensors, and many others. The other smart home technology is a smart metering system which is currently monitored and controlled by the utilities and other associated entities. These two systems are currently independent with no commercially available solution that integrates both into one. What are the advantages of integrating them? By supplying the user with real-time and historical data from the smart metering system, the user can then decide in what ways he can act or behaves so that his energy or gas usage is more adapted to his real needs. This way minimizing his utility costs and ultimately his carbon footprint. By improving these integrated measurements and controls, we not only save up in our home costs, but also improve our comfort, safety and security, and our lifestyle. These four categories and its derived benefits can be achieved by using a combination of the integrated technologies such as using energy time of use information to manage the schedules for our home appliances. For example, selecting a washing cycle during a low tariff period, or controlling the home heating system based not only on temperature and humidity sensors, but also on information from the smart metering system. How do we integrate both systems into one? The UK Smart Metering Implementation Programme and the SMAT specification has specified a device designated as CAD, Consumer Access Device, which is an access point to the smart metering system by the home user. Connector X is based on such a device, but it was designed not only to access the smart metering information, but also to fully integrate all smart home systems into one intelligent system. As we can see in the presented system architecture, Connector X integrates the most commonly used communication standards used in a smart home. To connect the smart metering system, we use Zigbee Smart Energy. And to connect to home devices, we either use Bluetooth Low Energy, Zigbee Home Automation, or Wi-Fi. We also have included Home Connect, which is a standard for connecting and controlling home appliances over Wi-Fi. Home Connect is supported by Siemens, Bosch, and a few other manufacturers. All the collected information is sent to AWS's cloud platform for storing, processing, and viewing, either through a web application dashboard, mobile application, or third-party application through an available secure API. After analyzing and comparing different cloud platform providers, we ended up selecting AWS because it offered a comprehensive set of services and features that had the needed requirements to achieve the initially proposed objectives, and an exciting roadmap to expand its capabilities, especially in topics like machine learning and AI. All this at a reasonable price. So of the comprehensive set of AWS services, we selected a few. For the back-end entry point, we use AWS IoT Core, which offers a secure and scalable connection based on MQTT and digital certificates. To store the data, we are currently using DynamoDB, which is a NoSQL database with almost limitless scalability and fast queries. There is a new AWS database service which might be more suitable, which is called AWS TimeStream, and could be an option for future developments. For data processing, we are using multiple serverless lambdas, and we hide all this behind a secure API by using AWS API Gateway. For AI machine learning, we are using SageMaker and Forecast. For voice controls, we use Alexa Skills. For authentication and secure requests, we use Cognito. And finally, the dashboard web application is supported in the AWS S3 bucket. The API is accessible not only by the web application, but also by our mobile application and authenticated third parties, as mentioned previously. For the user interface, we developed a web application and a mobile application. Being an R&D project with limited time and budget, we opted by including, for the time being, some features on one of the platforms but not on both, with the objective of presenting the maximum number of features. For example, we have included Home Connect and Forecast on the mobile application, but currently not on the web application. Nevertheless, both platforms have three distinct sections. The first section is focused on the smart metering data, where we can view meter information, real-time data, charts with instantaneous readings and historical data. We can also view the meter's current tariff calendar. The second section is focused on the smart home devices, where we can scan, add and manage the devices, view instantaneous readings, control different actuators and schedule multiple automatic tasks. The third and last section is for viewing and controlling home appliances. As previously mentioned, Connector X has fully integrated Home Connect, and all available features are accessible through Connector Access API. Besides using the common API, we can also schedule multiple automatic tasks for these appliances as we did for the smart devices, a feature unique to Connector X. By collecting all this data in the AWS database, we can then apply different AI and machine learning models by using AWS SageMaker and Forecast, so that we can predict future energy usage, identify appliances by their digital signature, detect anomalies, and ultimately feedback information to the Connector X to help its autonomous decision making. Currently, we already have energy usage prediction integrated into Connector X, but we believe that appliance identification through its digital signature unlocks a number of possible applications with valuable interest to the user. As part of the Connector X R&D project and in partnership with the University of Coimbra, we have also published a scientific article which studies, analyzes and presents the ideal machine learning model applied to a real set of energy data from the London area. This article is currently being reviewed by IEEE. And last but not least, I leave you with a quick view of the Connector X's final electronic hardware. Before we go on to a quick demo, are there any questions?
Jose, at the moment, we do not have any. We don't have any questions. So, could you please move to the next part?
Okay.
Thank you very much.
Okay. Just change the view here. I think you can see we have a panel here. With the smart meter, with a smart light and a temperature sensor, and we have a coffee machine from Siemens in this case, that uses Home Connect. So I'm just going to share the web page. I'm going to present a part of this, and then I'm going to pass then to a colleague of mine, which is also in the session, that can then do the mobile application demo. Just one moment, please. Can you see the screen?
Yes,
Okay.
we can.
Okay. The slides are presented very quickly the application, but I'll go through quickly what the web application has, and then I'll do a quick demo in terms of controlling. Okay, the first, as mentioned in the presentation, the first set of information is focused on the smart meter, where it retrieves all the possible information, from the meter through the Zigbee home network. For example, the total energy, active power, the current price, today's accumulated energy, the price of the accumulated energy, this week's accumulated energy, and the month's accumulated energy. This is read every minute, so this is we could actually be reading it more frequently, but you got to the conclusion 1 minute is more than enough in terms of frequency to read the meter and send it up to AWS for processing. We also have a chart. This was disconnected during the day, during the morning, so I'll just go for yesterday. So we have all the instantaneous readings from the meter, minute readings from the meter. So we have enough detail to identify different appliances at home. In this chart doesn't show that because it's just connected to a simple laptop during the whole day, so this is not quite clear, but we can identify quite clearly the different appliances in our home. And with this information, then it can be processed in AWS, as mentioned in the presentation, to identify different appliances, identify anomalies, verify, for example, or if our current maximum power is adapted to the installation's needs, or the installation's configuration, basically. In terms of our historical data, we have all the daily energy and costs, weekly data, energy and cost also, and monthly energy and cost. This is all information that is stored in the meter for a while, but it's then read every day to the ConnectX platform and sent to the AWS. So we not limited by the meter's limited memory, and we can view all the data collected in the past. We can also view the current meter calendar and its current tariffs. So we can see what are the ideal periods of the day for certain consumptions, and what are the current costs for each different tariff, and for specific special days in case it has specified or configured any special day or not. For the home device, we have the sensors. In this case, we have a temperature and humidity sensor. It's also read every minute, and we have information is updated. Can read the historical data for the sensors. Okay. This is, for example, temperature, humidity, and we also can see the controls for a switch. In that case, it's the smart light that we have connected to the ConnectX. For the smart light, we can switch it on, or quickly demonstrate the switching on. I think you can then view it as a certain delay for the first time that we switch on. Here we go, it's on at this moment. We can control its temperature and intensity. It really depends on what type of device we are controlling. We can configure different types of devices, different actuators with different types of settings. The device configuration, we can add different devices, look for different devices in our home network, add them to the home system, and control them by the system. And then in the schedule, we can define different timings, for example, to switch on the light at a specific time, control certain controllers at a specific time, every single day of the week. I can demonstrate quickly. I can, for example, the light we want to turn on starting from tomorrow. And for a week, during the week, and specific days of the week. And say we want to turn it on at noon, for example. Okay, and this will be set into the ConnectX's device, and it will control each device based on the schedule. Okay, here we go. And the web application, as I mentioned in the presentation, we don't have the Home Connect here, but we do have it in a mobile application. I'll pass quickly to my colleague Diogo so that he can present the mobile application and also using the Home Connect and Alexa too. Okay, Diogo.
Okay. Hello, everybody. So I will present the mobile application for Android for ConnectX. So let me try to share my screen. Okay, we have a login dashboard that is supported by Cognito, the secure interface for login of the ConnectX, and in here we have all the information that José have already shown, but for mobile application. So we have some meter related information that show us the ID of our device, the serial number, the customer ID, site ID, etc. Also the meter calendar with the tariff for the different seasons. In the related to the real-time information, we have the consumption demanded at each moment, and also we have the accumulated energy consumed for the day, the week, and the month, the current month. And we have also at the end of each line a target for a forecast that we have that we do not want to reach. So we have a forecast that is based on previous consumption, and the objective is, of course, get below this consumption. So we have also the chart with the consumption, where we can also select the period, let's say 12 o'clock until now, and we have the consumption or the demanded power that we have made for the period. We have also the historic charts, as in the web app, for the daily consumption, weekly consumption, monthly consumption. Our sensors. So again, the same sensors. In this case, we have the temperature sensor and the humidity sensor. The battery is the battery of the sensor, and we can see the history of each sensor. In this case, the temperature. Also, our actuators. So we can turn off the lamp. I don't know if we can see it. Yes, turn off, turn on. And also we have access to the schedule as the same way that we have in the web app. And we have also the 3 scheduled tasks that we had on the other side. Okay. The Bluetooth devices that we can connect. So we have the office sensor connected, also the office lamp, that are our 2 devices, and we can scan the other devices to connect them if they are to connect, of course. And finally, we have the connection to the Home Connect appliances. In our case, we have the coffee machine. So what we are doing is
Diogo, I need a coffee, please. Can you send me one?
okay, we have access to the coffee machine through the Home Connect interface. So this is our coffee machine. We have a brief resume of all the machine. We can get the list of what the appliance can do. We have a bunch of things that we can demand to the machine. So we can get an espresso. We can select the temperature, etc. Maybe key normal.
Normal, please.
Normal. Okay. The quantity we can have more or less quantity, and then the flow rate. Also, we can schedule the program. Okay, for the coffee machine, it may not make a lot of sense, but if we are talking about dishwasher machine or a laundry machine, it makes more sense. So I think that the coffee
the coffee is working. Yeah, thank you. In a few seconds to be done. Oh, sorry, it says it's insufficient beans. I have to put more beans or coffee beans there.
Okay. Okay,
Yeah.
so, and for the mobile application, it's pretty much this. It's a second way to interact with the ConnectX. And we have also a skill built for Alexa that allows us to retrieve the consumptions, act on the devices, and read the sensors. So we can try. How can I stop the share? Okay, we can try to stop sharing. Okay, so I think that we can try to get a value from Alexa. Let's say the consumed energy. Okay, we have an Alexa, an Echo Dot. Alexa, open ConnectX.
Welcome to the Connector X. How can I help you?
How is my energy consumption today?
You have already consumed 0.16 kilowatt hour today.
Turn off the office lamp.
Okay.
Thank you.
Goodbye.
Goodbye, Alexa.
Okay, and that's it.
Okay, thank you, Diogo.
Jose, I don't know if you want to continue from here.
No, I'll carry on from here now. Thank you, Diogo, for your presentation. Okay, any questions on the system or on architecture or anything?
Yeah, there are one or two questions. Let me. Sorry. Yeah. Yeah, the first question is from Michael. What do designers of systems need to do in terms of instrumentation, controls, and other system components to take maximum advantage of connecting technologies such as the ConnectX?
Well, there's a lot of things here. For the ConnectX, one of our main worries for the hardware design is to include different communications such as Zigbee, Bluetooth, Wi-Fi. So it could include most of the current technologies used in our home. For the home appliances, we looked for what was a standard. There was a few manufacturers out there with smart appliances, but we ended up choosing Home Connect because it had quite a broad adoption by different manufacturers. Siemens, Bosch, it was quite important manufacturers, and because the ConnectX interface is completely with their interface, so all that they supply we can support on our side, so we can evolve together with what the smart appliances can supply. So in that case, we are quite comfortable in terms of the evolution in how the system evolves in terms of the smart appliances using Home Connect. In terms of Zigbee and Bluetooth, really depends on how the devices implement the standard features. What we saw from Zigbee home automation, there's more of a standard. So as long as the devices follow these standards and they present the features using these standards, there's little or no changes on our side to control these devices. What we saw on the Bluetooth side, it's a bit more chaotic. You do have standard fields which you can use, and as long as the manufacturers use these standard fields, there's no issue on our side. If you do want to add a Bluetooth device that has a manufacturer-specific field, that will imply changes on our side to include these specific fields. As I mentioned, in Zigbee, it's clearer in terms of how do we integrate these things. In Bluetooth, as long as the standards are followed, it's easy on our side to integrate them immediately.
Thank you very much, Jose. Currently, we don't have any other questions. Before we go to the closing part of today's session, the workshop, I would like to ask if Helen could, we have a couple of questions that could be shared through Helen. Yeah, thank you very much. This is the second part of the poll. Could you please respond to these questions? Thank you very much. And here are the results. How would you rate your knowledge of smart technology for the home? Now 44% is rated as good. And for our second question, what do you think the potential is for energy saving through using smart technologies? And you have reached the excellent 56%. That's very good. Closing this session, and which is the last session of the workshop. We hope that you have enjoyed the workshop, and me, on behalf of the Energy House 2 team, would like to thank you very, very much for your participation, for your questions, and for your feedback. I just pass you to Joe. Joe, would you like to?
Yeah, thank you,
Thank you
Yanis.
very much.
Yeah, thank you, Yanis. Just like to say to everybody, thanks for attending. I think we've added a really good one there around smart meters, and we hope to be doing more workshops in the future. So keep an eye on our website, and you can see what we're doing and how we're getting along with the Energy House 2 project. Once again, thank you, and have a good evening. Goodbye.